All right, so we are talking in this section about rates of change, which is something that relates directly to derivatives, and in particular, I guess, we're going to be focusing on the relationship between position, velocity, and acceleration. So in order to sort of like get a feel for what this connection is, let's take a look at a function here that we've got graphed. But instead of imagining this purely abstractly in the xy plane, let's imagine that this function has a little bit more context to it. So we've got this function s of t here, the standard notation that our book uses for a position function. And when the book uses s of t to refer to a position function, in particular, t is going to refer to time in seconds, and the outputs are going to refer to position in some distance unit, frequently meters, but could also be feet, depending on the situation. But the long story short is, we've got a function here where what is normally playing the role of x, the horizontal axis, is t. So time is going to be here along the horizontal axis, and what is normally playing the role of y, the function value, in this case, this is going to be position, which is going to be, as mentioned, in meters or feet. So now what I want us to think about is, if we, instead of looking at this function, look at the derivative of this function, what information would that be giving us? Well, when you talk about the derivative of a function, that's going to be establishing a function to describe what? The slope of the tangent lines. So then you say, okay, well, if you look at any point along the original function and you evaluate the derivative, you have the slope of the tangent line. Now let's think here for a second. What would the slope of the tangent line here be in terms of? Because you know the slope of any line is just some change in y over change in x. And in particular, the change in the vertical axis for this problem is not just any change in y, but as we mentioned, change in position. So this is going to be some, let me write this out in words, change in meters, change in position, and denominator, change in x. Well, actually, in this situation, the horizontal axis is not the x-axis, but playing the role is the t-axis, which is some increment of time. So here we have a change in seconds. And whenever then you evaluate this measure and you take the change in meters divided by the change in seconds, you get some number which is in meters per second. And now here's the thing to think about. While your original function measured position at any time, where are you? The tangent line, the derivative, is measured in terms of meters per second. How fast are you going? So in other words, when we start with the position function here, s of t, and we take a derivative, this derivative is with respect to time, which is giving us this what? This meters per second value. That's going to give us something that measures speed. Let's call that velocity, the standard sort of physical word to describe a rate of change in terms of position. So position is measured in meters, velocity measured in meters per second. And now, here's something to think about as well. Because you can take this function, s of t, compute its derivative, and get velocity. And as we saw, the units make perfect sense there. But now, velocity itself is going to be a function. Because you know that whenever you take the derivative of a function, you get another function back in return. So here now, we've got our velocity function. What can you do to the velocity function? Well, like any function, you could try to find its derivative. And then one question would be, well, if you took the derivative of the velocity function, what kind of function would you then be? And to think about that, well, let's just think, okay, rather than dealing with our position function, let's instead think about our velocity function. Velocity is not measured in meters. That's going to be in meters per second. Should our original position have been in feet, this would now be feet per second. So be it. And well, here, rather than dealing with the position function, now we're going to be dealing with our velocity function. So when you look on the axes, while the velocity function is still a function of time, because of course, whatever our original function was in terms of the t variable, when we take its derivative, the derivative will still be in terms of the t variable. So velocity is still a function of time, measured in seconds, but now, along the vertical axis, we no longer have a position, we have a velocity. Okay, now, let's try to find the slope of the tangent line in this case. As any slope is, it's rise over run, and as any derivative is, it's giving you the measure of the slope of the tangent line. So the question then becomes, well, what's the unit on this line if we're looking with the velocity function? Well, the change in y is going to be some change in vertical position. That's going to be, in this case, change in velocity, change in meters per second. And now, what's the change horizontally? The change horizontally is along the t-axis. That's giving us a change in seconds. And whenever you compute this out, whatever is the rise in meters per second and the run in seconds, when you divide that out, you're no longer going to be in meters per second, but now meters per second squared. And if you recall back to some notion of physics or something like that that you may have encountered in your past studying of science, just as position is measured in meters and velocity is measured in meters per second, there is a corresponding measure that's in meters per second squared, and that corresponding measure is acceleration, the change in velocity. And we could call that A of t, A for acceleration, just like V for velocity, and I guess we use S for position, but I guess that's the book's terminology. But here's the long story short. The long story short is if you imagine a function being a position function, when you take the derivative and analyze the units on the slope, you get meters per second, which yields a velocity function. And now, if you think of your velocity function, and you again take a derivative and analyze what the slope is of the tangent lines to that velocity function, now you're going to be getting, well, upon taking that derivative, a function that's in meters per second squared. That's an acceleration function. Long story short, position function, take a derivative, velocity function. Velocity function, take a derivative, acceleration function.